Okay, so today we are going to start exercises from electricity and magnetism. And let's start with exercise number 4. Exercise number 4. Exercise number 4. A ring is made of thin wire and has radius r and charge q. I'll write radius as this letter. Radius r and charge q. Radius r and charge q. Find the modulus of the electric field intensity of the on the axis of the ring as a function of the distance L to the center of the ring. Investigate obtained dependence when L is much bigger than R, and define the maximal value of the electric field intensity and corresponding distance L. Okay, so we have system of electric charge. I'll try to draw this on the screen. So we have some charged ring. The ring is perpendicular to the screen, and it can be drawn like here. I'll set some coordinate axis. For example, here X, Y, and Z. X, Y, and Z. So X is the axis of the ring. So we have to find electric field intensity on the axis X. Maybe you have some ideas how to do this. Maybe you have some ideas. No ideas. Okay. We can use the definition. We can use the definition of electric field intensity. I mean the formula of electric field intensity for point charge, and superposition principle. So let's use this formula. But to use this, I'll use some infinitely small part of the ring. Maybe it will be better to show this in this way. Infinitely small part of the ring. It can be it can be shown like here. It is infinitely small charge dq. And this infinitely small charge produces electric field with intensity dE. With intensity dE. Produces electrostatic field with intensity dE. With intensity dE. Okay, how can we find the modulus of the intensity dE? Maybe someone can remember this. Maybe someone can remember. Nobody. We can use formula. We can use formula for electric field intensity of the point charge. Maybe you can remember this or to find this formula in your notes. Yes, okay. Okay, it looks well. Okay, and good. And if we use vector form here, we should put vector above the letter. And in the left side we have differential. And if we have differential, in the right side we should also write differential dqi. Okay, this is correct formula. But it is necessary to make some changes. First of all, um, it is better to use distance from dq to the point where we want to calculate electric field. So we can set ri as 0, and we can also use scalar form. So we can write that dE is the same as the modulus of dE, and it will be it will be 1 divided by 4 p epsilon 0 dq divided by r to the power of 2. And I have set Ri as 0. Ri as 0. So we can use this formula. And what is necessary to do? It is necessary to define. R to the power of 2 squared r. R is here. This is r. A little letter r. And we know that the radius is equal to big letter r, and the distance of the ring, from the ring to the point where we want to calculate electric field intensity is equal to L. The ring is perpendicular to the screen. So how to find this? How to find this this value, this distance r? So if you look if you look carefully at this picture, you can see that we have the right triangle. Here we have right triangle. I'll draw this separately. This right triangle. With sides R, L, and little r. So we have this triangle. On this picture. So how to find a little r? How to find this? It is from geometry. No, it is not equal to r. Okay. R sinus. Maybe r sinus, but it will be not product. We should divide r by sinus. Divide r by sinus, and not 90 degrees. Let's use Pythagoras theorem. how to find little r from big R and L. So let's remember the connection between sides of the right triangle. Between sides of the right triangle. I'll draw. Oh yes. Okay. Okay. This is what we need. Okay. Okay. I agree. I agree. This is what we need for the exercise. Okay, and so we have to we have to we have to calculate this field. So the field of the whole ring, will be the sum of fields produced by all charges dq. So no d, it will be e. E is equal. E is equal to integral of all these differentials dE. dE we have here. And it will be equal. It is equal to dx I plus d e y j plus d e z k. d e z k. We have written dE in components. And if you look carefully at the system, we can see that system has symmetry. System has axial symmetry. The axis of symmetry is x-axis. X-axis is the axis of symmetry, or axis of the ring is the axis of the symmetry. The axis of the symmetry. And according to this, we have, for example, we have the same charge dq here. We have the same charge dq here. So this dq and this dq produce electric fields, and these electric fields after adding will result that here we have zero. Because of the symmetry. Because of the axial symmetry of the ring. For example, it is not necessary to use this, but this can make This can make our solution simpler. This can simplify our solution because the only one component of the vector is left. So, the problem becomes simpler. The problem becomes simpler after this. After we noticed the symmetry of the system of charges. Okay, do you have any questions? Do you have any questions? No questions. No questions. Okay. 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 So DEX. What is DEX? DEX. I'll try to draw this. I'll try to draw this here. I'll try to draw this here. DEX is a part of the vector DE that has the same direction as x-axis. So it is here DEX. Here we have DEX. DEX. And how to find this? How to find DEX from DE? From DE. So we need to find DEX. DEX. So this is equal to if here we have the angle alpha, and how to find DEX from DE? How to find DEX from DE? What should be here? What should be here? If you want to find DEX from DE. No ideas. Okay, DEX, if DEX is the projection of DE on axis X, so it can be expressed. It can be calculated via cosine. So it is DEX multiplied by cosine of alpha. Okay, and how to find this cosine of alpha? Angle alpha is here. How to find cosine alpha? How to find this? Maybe somebody knows this from geometry. Nobody knows. It is equal to L. Yes. L divided by R. Okay. 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 I agree. I agree with this. L divided by R. Okay, that's correct. That's correct. And this is equal. This is equal to L divided by square root of this. And here we know L and we know R. And we know R. Okay. Okay. So we have from this we have that it is equal to uh, 1 divided by 4 p epsilon 0 4 p epsilon 0 dq divided by r to the power of 2 and multiplied by L divided by R. And this is equal to 1 divided by 4p epsilon 0 4p epsilon 0 4p epsilon 0 here we have dq divided by L here divided by R to the power of 3. And this is equal to 1 divided by 4p epsilon 0 4p epsilon 0 L dq divided by square root L squared plus R squared under the root and to the power of 3. Okay, do you have any questions? Do you have any questions about this? No questions. No questions. Okay. Okay, so this is great. This is great. If there is no questions, this is great. We can now use this. We can now use this. We can use this, and from here we have that. We have that E is equal to modulus of E, and this is equal to the integral of d e x from 0 to e, from 0 to e, and this is equal to this is equal to this is equal to integral of 1 divided by 4p epsilon 0 L dq divided by square root plus r to the power of 2. Okay, what about integral limits? What about integral limits here? What about integral limits? Can someone define them? We need to take into account the whole ring, the whole charge of the ring. So how to define integral limits in this case? Yes, from 0, and the upper limit will be the whole charge of the ring. Yes, okay, this is correct. This is correct because in differential we have charge. So in integral limits we should also have charge. And I'll make this sign. Above the Q to make different signations. At the differential and in integral limits. So 1 divided by 4p epsilon 0, L and R don't depend on Q, so it can be written outside the integral. 4p epsilon 0, L divided by this to the power of 3, integral from 0 to Q dq. So can we calculate this? It will be 1 divided by 4p epsilon 0. Here we don't have any changes. L plus R square root to the power of 3. And what will be here? What is here? Okay, okay. Okay, it will be Q. It will be Q. I agree. I agree. So we have found electric field intensity on the axis of the ring. We have found electric field intensity, and now I have to clean some place. I have to clean some place on the screen. I have to clean some place on the screen. So we have obtained that the modulus of electric field intensity on the axis of the ring is equal to 1 divided by 4 p 4p epsilon 0 multiplied by LQ divided by square root from squared L squared R sorry, to the power of 3. Okay, this is the modulus of electric field intensity. The modulus of electric field intensity on the axis of the ring. Okay, and what about electric potential? It is not asked in the exercise. It is not asked in the exercise, but it will be useful for us. It will be useful for us to find electric potential. So how to use how to find this? How to find this? In the similar way as it was done here. In the similar way. As it was done for electric field intensity. We have similar formula. Yes. Okay. This from R0 to R vector. This is correct, but it will not be useful in our case. It will not be useful in our case because we don't know electric field intensity as function of coordinates or as function of radius vector. So it would be better to use another formula. And here we don't have D in this case. Here we don't have D. Yes, this formula is correct. But we need to use something like this. The formula of potential of point charge. Formula of potential of point charge. Can someone remember this formula? The potential of point charge. I mean something like this. 1 divided by 4p 4p epsilon 0 4p epsilon 0 dq divided by r. I mean this. It is electric potential of point charge. 1 divided by 4p epsilon 0 dq divided by a square root of no, sorry, it will be L plus R plus squared R. Okay, do you have any questions? No questions. No questions. Okay. Okay, so if you don't have any questions, we can find electric potential on the axis of the ring. So electric potential phi is equal to the integral from 0 to phi from 0 to phi d phi, and this is equal to the integral from 0 to q in the same way as it was done here. In the same way as it was done here for the electric field intensity. 4p epsilon 0 dq divided by square root L squared R squared. So from here we have 1 divided by 4p epsilon 0 4p epsilon 0 q divided by square root L squared plus R squared. Plus R squared. Okay, do you have any questions? Do you have any questions? No questions. No questions. Okay. That's great. That's great. if there is no questions. So we have obtained electric field intensity and potential on the axis of the ring. The axis of the ring. Potential is equal to 1 divided by 4p epsilon 0 4p epsilon 0 and so we have solved the first part of the exercise. So let's clean some place. Okay. Okay. Well, the next part is to investigate obtain dependence when L is much bigger than R. L is much bigger than R. It is quite simple. It is quite simple to do. In this case, we can write that E is approximately equal to 4p epsilon 0, 4p epsilon 0, L Q, the modulus of no, it will be more useful to write like this. Square root, and it is equal to 1 divided by 4p epsilon 0, 4p epsilon 0, L Q modulus of L to the power of 3. But L is distance. L is a distance, so it is always positive. It is a positive value. So the modulus of this value is equal to this value. LQ divided by and after simplifying 4p epsilon 0 Q divided by L to the power of 2. So we have obtained formula that looks similar to the field of point charge. So from this formula we can make a conclusion that from very long distance the ring looks like a point, and I think it is what can be expected. Okay, do you have any questions? Do you have any questions? No questions. Okay, so how to define the maximal value of electric field intensity? How to define a maximal value, the maximal value? we can find it using calculus. What can you remember from calculus? What can you remember from calculus? What can you remember from calculus about the maximal value of the function? For maximal or minimal value of function, the derivative of the function is equal to 0 or does not exist. So we have to find this derivative. dE by dL is equal to let's try to find this. It will be 1 divided by 4p epsilon 0 4p epsilon 0 q divided by square root from squared L squared R to the power of 3, and the second add. So square root to the power of 3 is the same as power of minus 3 divided by 2. So we have minus minus 3 divided by 2, 1 divided by 4p epsilon 0, 4p epsilon 0. Here ql divided by square root L squared R squared to the power of 5. To the power of 5. Because 3 divided by 2 minus 1 is equal to plus 1. No, sorry, again, it will be minus 5 divided by 2. So because of this we have 5 above the square root, and under the square root we also have function from L. So here we have to write 2L. Okay, do you have any questions? Do you have any questions about this derivative? No questions. No questions. Okay. Okay. If there is no questions, we have 1 divided by 4p epsilon 0, 4p epsilon 0 q. I can write q divided by 4p epsilon 0, and here Here we have here we have I have forgotten something or not. I have forgotten. No. Okay, it's everything is okay. 1 divided by square root plus r squared minus 3l and square root plus r to the power of 2, 5, and from here we can make the mutual denominator. We can make mutual denominator, and from here we have obtained that this is equal to 4p q divided by 4p epsilon 0, 4p epsilon 0, and multiplied by L squared plus R squared. So you can see here we have quite massive, quite difficult algebraic transformations. So it is necessary to cope with this. To the power of 5. And this is equal to q divided by 4p epsilon 0, 4p epsilon 0. In a numerator, we can make some simplifying. It will be r squared minus double L squared. And divided by square root plus r squared plus r squared to the power of 5. To the power of 5. Okay, and according to the calculus, when E is the maximal, is maximal, it will be 0. It will be 0 when electric field intensity is maximal. Okay. Okay, the question is how to solve this equation. How to solve this equation? How to solve this equation? Do you have any idea? It will be 0. This expression will be 0 when the numerator is equal to 0. So from here we have r to the power of 2 minus double L to the power of 2 is equal to 0. And from here we have that L is equal to plus or minus r divided by square root from 2. But L is a distance. L is a distance, so it cannot be negative. It cannot be negative. So we have to leave only positive value of the root. Only positive value. So this is the root of the equations. This is the distance. This is the distance of the distance where we have maximal value of electric field. Okay, do you have any questions? Do you have any questions about this? No questions. No questions. Okay. Okay, if there is no questions, I need to clean some place on my screen. To clean some place on my screen. And how to find maximal value of electric field is necessary to make substitution. EM is equal to 1 divided by 4p epsilon 0 divided by 4p epsilon 0 r divided by square root from 2 q square root r plus r squared to the power of 3. So let's simplify this expression. This expression it is equal to 1 divided by 4p epsilon 0 4p epsilon 0 rq divided by square root 2 square root of 3 r to the power of 2 divided by 2. And this is equal to 1 divided by 4p epsilon 0 it is r q divided by square root from 2 square root from 3 r squared, and this is equal to 1 divided by 4p epsilon 0 4p epsilon 0 square root from 2 to the power of 2 RQ and square root from 27. 27 is 3 to the power of 3. Here the modulus of R. So 1 divided by 2p epsilon 0 R Q RQ square root from 9. R is positive, so we can write it without modulus. So it will be Q divided by 6 square root from 3 p epsilon 0 R to the power of 2. Okay, do you have any questions? Do you have any questions about this? Do you have any questions? Okay, dear students, can you hear me?
Yes, teacher.
Okay. And so you don't have any questions. Okay, if everything is clear. Okay. Yes. Okay, I see. I see. So I need to clean some place on the screen. So we have solved the exercise number 4. It was difficult. But we have coped with this. Let's solve exercise number 5. The next exercise is number 5. Is number 5. A system consists of a thin charged wire ring of radius r and a quite long uniformly charged thread that is placed along the ring's axis. So we have thread that is on the axis x. One of the thread's ends is in the center of the ring that has charge q. So ring is the same as it was in previous exercise. A unit of thread's length has charge lambda. Or lambda has charge lambda. So lambda is linear density. Of the linear charge density is lambda. Find the force of interaction of the ring and the thread. So we have to find the force of the interaction between thread and ring. Thread has one end one end in the center of the ring, and the second end is very far from the ring, and the thread is placed on x-axis. Okay, do you have any ideas how to find the force of electrostatic interaction between the thread and the ring? How to find this? Okay, it is possible to suggest at least two ways to solve this problem. The first way, but it is not good in this case. The first way is to use Coulomb's law of for electrostatic interaction. According to this, we can write that force of electrostatic interaction is equal to I will maybe without vector. It will be 1 divided by 4 p epsilon 0 product of dq t. dqt is some charge of the element of the thread, and divided by r to the power of 2. So we can use Coulomb's law, but here you can see two differentials, dq and dqt. So it is necessary to calculate double integral. It will be double integral, but it is possible to use simpler way. It is possible to use simpler way in this case. What is this way? As you can notice, we have already found electric field intensity. And we can find dF, differential of force, from formula E multiplied by dq t. dqt is charge of the thread. So it is somewhere here. Here is a small charge dq t. As you can remember from our theory, from our lectures, force of electrostatic interaction between electrostatic field and point charge can be found by formula. That looks like this. And here we have used this formula. Okay, so we have calculated electric field intensity, and it is necessary to define dqt. It is necessary to define dqt from linear density of the charge. From linear density of the charge. From linear charge density of the thread. How to do this? Do you have any ideas? How to find this differential? Because from the description we have lambda, we have linear charge density. So how to find this? Okay, no ideas. Maybe you can remember from school. Can you remember from school? Density, simple density of mass is equal to mass divided by volume. And from here we have mass is equal to density multiplied by volume, where rho is volume density. Rho is volume density. And from here we can find that differential dm is equal to rho multiplied by dv. So the similar situation we have with the linear density. With linear density we have similar situation, and according to this we can write that this elementary point charge is equal to lambda multiplied by dl. Okay, do you have any questions? Do you have any questions about this? Oh, okay, let's make a substitution. So from here we have 1 divided by 4p epsilon 0, 4p epsilon 0, L q L q divided by square root L to the power of 2 plus R to the power of 2 and lambda dl. Lambda dl. And from here we can write that force of electrostatic interaction is equal to the integral from 0 to f df, and this is equal to integral 1 for p epsilon 0 L q lambda d L divided by square root squared plus r squared to the power of 3. Okay. The only step is left is to define integral limits. Can someone of you define the integral limits? It will be from one end of the thread to the other end of the thread. So how to define the integral limits in this case? How to define the integral limits in this case? No ideas. Okay. Left end of the thread is in the center of the ring. As you can see from the picture, the center of the ring has coordinate on x-axis has coordinate 0. And what will be the upper limit of the integral? Upper limit here. What will be the upper limit of the integral? L. Okay, but we don't know the length of the thread, but we know that it is quite long. It means that the thread is very, very, very long. The thread is very long. So how to define very, very long thread mathematically? It's very long. It can be. It means that it is infinitely long thread. So yes. Okay. It is infinitely long thread. Okay, so what is left? It is necessary to calculate this integral, and after calculating this integral, the problem will be solved. So, but I have to clean some space on the screen. I have to clean some place. So I'll draw this here. So all constants can be written outside the integral. One, it here we have. Maybe it will be q lambda. Integral from 0 to infinity. dl divided by L L squared plus R squared and it can be written as Q lambda divided by 4p epsilon 0 limit k to infinity the integral from 0 to k L d L divided by square root of L squared plus R squared to the power of 3. So it is necessary to calculate the integral. So let's do this. Integral from 0 to k L d L square root plus R squared to the power of 3. How to calculate this? It is necessary to make some change, to make some transformation. So I can suggest one substitution. Substitution t is equal to this. According to this substitution, differential dt is equal to 2 L d L, and from here we have that L d L is equal to d t divided by 2 and t of L equal to 0 will be R to the power of 2, and t of L equal to k will be squared k plus squared R. So from here we have, let's substitute LDL by dt divided by 2. It will be 1 second. From R squared to T squared plus R squared plus R squared, and it will be d t divided by square root of t to the power of 3. And we have from here it will be 1 second. minus 2, 1 divided by square root from t squared plus r squared is equal to minus 1 divided by plus r squared minus 1 divided by r under the root. And it will be 1 divided by r minus 1 divided by square root from key squared plus r squared. Okay, do you have any questions? No questions. So we have calculated the integral. So we have q lambda 4 p epsilon 0 limit k to infinity k to infinity k to infinity k to infinity so let's return here. It is better to rewrite this. So here we have k kl plus r, and here 1 divided by r minus 1 divided by square root plus r squared. Okay, and after calculating this limit, we have obtained that it is equal to q lambda divided by 4 p epsilon 0 r. This is the answer. Okay, do you have any questions? Do you have any questions about this? No questions. Okay, if you don't have any questions, the next homework will be number 2 and number 3 from electricity and magnetism. Number 2 and number 3. I'll write this from electricity and magnetism. From electricity and magnetism. Okay, do you have any questions? No questions. Okay, so thank you for your attention. I hope to see you next week.
See you, teacher.
Thanks,
Have a
teacher.
nice
Goodbye.
day.
See you.